Welcome to Lecture 5. Quantum mechanics is a probabilistic model where events occur with some likelihood. In today's preparation lecture, we will examine concepts in probability so that when we examine quantum mechanical problems, we will have all the tools necessary to quantify them. This lecture is broken down into 3 parts. In the first, we're going to go over some definitions over the various aspects of the probability theory that we will be using. And then we're going to apply these into discrete distribution examples, and then finally to continuous distribution examples. Probability theory is a methodology which allows for the quantification of how likely an event is set to occur. It can be based on data. For instance, the ages of a sample of people in a room could be recorded. Based on that, we could answer some questions about this group of people. What is the probability of being 15? What is the most probable age? What is the average age? What is the average of the squares of the ages? What is the standard deviation of the ages? The answers to some of these questions are pretty evident. The probability of being 15 is 1 over 14, and the most probable age is 25. We will spend this lecture defining how to answer these questions. Consider an experiment such as flipping a coin, with n possible outcomes, each with a probability p sub j of occurring, where j could be 1, 2, and so on up to n. In this case, j represents each outcome. So for the coin example, j is only equal to 1 or 2 since there are only 2 sides to a coin. If the experiment is repeated an infinite number of times, then the probability of an event j occurring is the limit as n goes to infinity of n sub j over n, where again j is just equal to a numerator or an integer that defines which event we're talking about. In this definition, n sub j is just the number of times that event j occurs, and n is the total number of repetitions of the experiment. So a simple example of this goes back to the previous slide where 5 people out of 14 were 25. Ignoring the limit for a second, n sub j is equal to 5, meaning we had 5 events that we had someone being 25 years of age out of a total of n, 14 people. So the probability of being 25 is 5 over 14. Now the limit just means that if we wanted to get a true probability, we would need a sample that is infinitely large. For instance, flip a coin 10 times. If it's a fair coin, then you should land on heads 5 times, and you should land on tails the other 5 times. However, if your sample is only 10, then it may not do that. If you were to base the probability of landing on heads or tails on a low sample size, you may not conclude that it's a fair coin. However, if you increase the number of flips you measure to 100, 1,000, 10,000, and so on, then the coin, and if the coin is fair, then you will get closer and closer to a 50-50 split. That's what the limit represents, that if you sample an infinite number of events, you would get the actual probability. Let's define a couple of other things. Because the number of times that a specific event occurs must be greater than or equal to 0 and less than or equal to the total number of events, the probability that a specific event occurs must lie between 0 and 1. When the probability that a specific event occurs is 1, then we say that the event will occur with 100% certainty, and when it's equal to 0, then the event is impossible. In addition, because the sum of all the times each event occurs is equal to the total number of events, then we have the normalization condition, which means that the probability that one of the events occurs is a certainty. For instance, going back to the age example, the normalization condition says that since there were only 14, 15, 16, 22, 24, and 25-year-olds in the room, the probability that if you pull someone out of the room and ask their age, it is certain that you will get a 14, 15, 16, 22, 24, or 25-year-old. Let's now start to use these definitions to determine some useful values. In quantum mechanics, the average value is called the expectation value. The average value of a quantity is denoted by that quantity being enclosed by angular brackets, and it's the sum of each event, x sub j, times the probability of each event occurring, p of x sub j. So for the birthday example, the expectation value of the age of a person in our sample is the sum of the age times the probability of someone being that age. In our data, the expected value is 21. Another useful quantity is the second moment, or the average of the squares of a set of events. The second moment is denoted as the expectation value of x squared. and it's equal to the sum over all possible events of the value squared times the probability of the event itself. Again, using the data from before about the ages of people in a room, the average of the squares of ages is the sum of the square of each age times the probability of finding that age. For our data, the answer is 459.6. To determine the standard deviation or spread of some data set around the average, it's logical to find out how far each value is from the average. This might be defined as the value itself minus the expectation value, and we have that equal to delta x sub j. But the average or expectation value of delta x would be 0. To solve for this, we take the square before averaging. And so this is denoted as sigma squared is equal to the expectation value of delta xj squared, which we can also write as the expectation value of xj squared minus the expectation value of xj all squared. Sigma squared is called the variance of the distribution. The standard deviation is simply the square root of the variance. We have been primarily looking at discrete distributions, where only certain values of x sub j are allowed. Examples of these include flipping a coin or the birthday data at the start of the lecture. In this course, we will be using continuous distributions, meaning that all values between two numbers, say a and b, are allowed and have a probability associated with them. This means that the probability of a continuous set of events occurring between x and an infinitesimally small distance to the right of it, dx, is equal to the probability of the events occurring times that tiny distance dx. To widen the range that we want to know the probability of something happening, then we take the integral over that range. Remember that an integral is just a continuous version of taking a sum. So, the total probability of a set of events between a and b is the integral evaluated between a and b of p of x dx. We can also rewrite all the values we just defined for discrete distributions for continuous distributions. The integrals are over the ranges of minus infinity to infinity because, as a general rule, all possible events denoted as x must be considered. Frequently, we can truncate the bounds of these integrals since we know that over large ranges the probability will be 0 and therefore does not need to be considered.